Welcome to the continuation of our series on using rigorous methods to analyze long transmission lines. In our previous video, we explored the approximate method, also known as the convergence series method or complex angle method. We applied hyperbolic functions, specifically the hyperbolic sine and cosine, which were derived from the line's impedance, admittance, and conductance. These functions helped us solve for the sending end voltage and current of the transmission line. In today's episode, we'll continue in the same vein, but this time we'll be using the exact method to analyze our long transmission line. We will use this approach to derive the ABCD parameters of a long transmission line. The parameter derived will be used to calculate out the sending end voltage and current of the line. Finally, we will use the sending voltage and current of the line to determine the line regulation and the efficiency of the line. So without any further ado, let's get started.
We will continue from where we left off last time, but this time, we will begin by analyzing the problem of a transmission line using the exact analysis approach. So let's examine the following scenario. A three-phase transmission line, 320 kilometers long, has the following parameters. The resistance per phase per kilometer is 0.075 ohms. The inductance per phase per kilometer is 0.48 times 10 raised to power minus 3 Henry. And the capacitance per phase per kilometer is 3.38 times 10 raised to power minus 9 farads. 1. Determine the exact ABCD constants for the above parameters. 2. Use the ABCD constants to calculate the sending end voltage and current when the line is delivering a load of 480 megawatts at a 0.87 power factor lagging, while the receiving end voltage is held constant at 330 kV. 3. Finally, determine the regulation and efficiency of the line.
Let's begin out by looking at the given parameters. Inductance is equal to 0.48 times 10 raised to power minus 3 Henry. Capacitance equals 3.38 times 10 raised to power minus 9. Resistance equals 0.075 ohms. Now we are tasked with calculating the impedance of the circuit. Impedance, in this case, it is given by resistance plus J times angular frequency times inductance, where angular frequency equals 2 pi f and when f equals 50 Hz. So when calculated out, omega equals 2 pi times 50 equals 314.16 rad per seconds. Now substitute into the impedance formula. It will now be 0.075 plus J, 314.16, times 0.48 by 10 raised to power minus 3. This will equal to 0.075 plus J, 0.150, and when multiplied by 320, this will equal to 24 plus J 48. Now, convert this rectangular form to polar form. This will be equal to 53.66 at an angle of 63.43 degrees ohms.
We can also calculate the admittance of the transmission line. Admittance is given by the sum of conductance and the imaginary component, which is J omega C. To calculate this, we start by recalling that omega is equal to 2 pi f, where f is the frequency. So for a frequency of 50 Hz, we get omega equals 2 pi times 50 equals 314.16 rad per seconds. Now we multiply omega by the capacitance, which is 3.38 times 10 raised to power minus 9. So omega C is equal to 314.16 times 3.38 times 10 raised to power minus 9. This is equal to J 1.061 times 10 raised to power minus 6s per kilometer. Next, we multiply the result by the total length of the transmission line, which is 320 kilometers. So line admittance will now equal to J 1.061 times 10 raised to power minus 6 times 320. This will equal to J 3.39 times 10 raised to power minus 4s. Thus, the total admittance of the line is Y equals 3.39 times 10 raised to power minus 4s at an angle of 90 degrees.
Now that we have calculated the values for impedance and admittance, we can proceed to calculate gamma L. We begin by inserting the values into the following equation. Gamma L is equal to square roots open brackets 53.66 at an angle of 63.43 degrees close bracket times open bracket 3.39 times 10 raised to power minus 4 at angle of 90 degrees closed brackets. Multiplying these values results in square root of 0.01819 at angle of 153.43, which is the summation of both angles. Upon further simplification, we get gamma L to be equal to 0.134 at an angle of 76.71. Finally, converting this to rectangular form, gamma L will be 0.0309 plus J 0.1311.
Now that we know gamma L, we can calculate the hyperbolic cosine or cosh gamma L, which is expressed as cosh 0.0309 times cos 0.1311 plus sin 0.0309 times sine 0.1311. Before we start using our calculator, we need to make sure it's set to radian mode. Once the calculator is set, we can enter the values and calculate each term as follows. 1.0004 times 0.9914 plus 0.0309 times 0.1307. The result for cosh gamma L is approximately 0.9917 plus J 0.004. When this is converted to polar form, the magnitude is 0.9917 and the angle is 0.004 radians, which is equivalent to 0.23 degrees. Therefore, cosh gamma L is 0.9917 at an angle of 0.23 degrees.
To evaluate the hyperbolic sine, we will use the same approach. The expression we are working with is sin open bracket 0.0309 close bracket times cosine open bracket 0.1311 close bracket plus cosh open bracket 0.0309 close bracket times sine open bracket 0.1311 close bracket. The resultant of the above when the calculator is punched will be open bracket 0.0309 close bracket times open bracket 0.9914 close bracket plus open bracket 1.0004 close bracket times open bracket 0.1307 close bracket. When simplified, we get 0.0306 plus J 0.1307. Now, converted from rectangular form to polar form, the magnitude is 0.1342 and the angle is 1.34 radians, which is equivalent to 76.82 degrees. Therefore, sin equals 0.1342 at an angle of 76.82 degrees.
Now that we have determined the hyperbolic values for both cosine and sine, we can proceed to substitute them into the ABCD parameters. For the A and D parameters, the value is 0.9917 at an angle of 0.23 degrees. However, this does not apply to the B and C parameters. For the B parameter, it is represented by the impedance sin gamma L. Substituting the values, we get the following expression. Square root of 53.66 at an angle of 63.43 degrees, all over 3.39 times 10 raised to power minus 4 at an angle of 90 degrees. All times open bracket 0.1342 at an angle of 76.82 degrees close bracket. On the left-hand side, the result of these calculations is open bracket 158,289.08 at an angle of minus 26.57 degrees. Multiplying this by the right-hand side, the value of parameter B becomes 53.39 at an angle of 63.54 degrees.
For the C parameter, it is calculated as the reciprocal of the impedance multiplied by the hyperbolic sine of gamma L, which is expressed mathematically as this here. We are given the values to substitute into this formula here. The impedance is 397.85 at an angle of minus 13.28 degrees. The hyperbolic sine term gamma L is 0.1342 at an angle of 76.82 degrees. Now, substituting these values into the equation, parameter C is equal to open bracket 397.85 at an angle of minus 13.28 degrees closed bracket times open bracket 0.1342 at angle of 76.82 degrees close bracket. Now this involves two complex numbers, one representing the impedance and the other representing the hyperbolic sine term. To simplify, we calculate the reciprocal of the impedance, which is 1 all over 397.85 at an angle of minus 13.28 degrees. This gives us 2.513 times 10 raised to power minus 3 at an angle of minus 13.28 degrees. Next, we multiply this result by the second term, which is 0.1342 at an angle of 76.82 degrees. Multiplying the magnitudes 2.513 times 10 raised to power minus 3 times 0.1342 is equal to 3.37 times 10 raised to power minus 4, and adding the angles, 13.28 degrees plus 76.82 degrees equals to 90.1 degrees. Thus, after multiplying both terms, the resulting C parameter is equal to 3.37 times 10 raised to power minus 4 at angle of 90.1 degrees.
Great! Now that we have successfully solved question 1 by determining the ABCD parameters of the transmission line, we can now move on to question 2. This question requires us to use the ABCD parameters to calculate the sending end voltage and current of the line. Before doing that, it's important to first calculate the receiving end voltage and current. We are given that the line-to-line receiving end voltage is 330 kilovolts. To find the phase voltage, we divide this line voltage by root of 3. This will give us a receiving end phase voltage of approximately 190,525.588 volts. Next, to find the receiving end current, we use the formula for three-phase power, which is power divided by the square root of 3, multiplied by voltage, and multiplied by the power factor. Substituting the given values, which are 480 megawatts of power, 330 kilovolts of line-to-line voltage, and a power factor of 0.87, when simplified, we will get a receiving end current of approximately 965.26 amperes. With both the receiving end voltage and current now known, we can use the ABCD parameters to calculate the sending end voltage. According to the transmission line equation, the sending end voltage Vs is equal to parameter A multiplied by the receiving end voltage, plus parameter B multiplied by the receiving end current. When we substitute the values for A, B, the receiving end voltage, and the receiving end current, we end up with two complex numbers in polar form. The first term, which is parameter A times the receiving end voltage, has a magnitude of approximately 188,944.23 volts at an angle of 0.23 degrees. The second term, which is parameter B times the receiving end current, has a magnitude of about 51,535.23 volts at an angle of 34 degrees. To add these two complex quantities together, we must first convert them from polar form to rectangular form. After conversion, the total sum is approximately 231,667.34 plus J 29,576.60 volts. Finally, we can now convert this result back into polar form, which gives us the sending end voltage as approximately 233,547.71 volts at an angle of 7.27 degrees.
In the same vein, we can now calculate the sending end current Is, which is equal to parameter C multiplied by the receiving end voltage Vr, plus parameter D multiplied by the receiving end current Ir. When we substitute the values into the equation, we get Is as this, and when simplified, Is will now equal to open bracket 64.207 at an angle of 90.1 degrees close bracket plus open bracket 957.24 at an angle of 29.31 degrees close bracket. To add these two phasors, we first convert them from polar form to rectangular form. After conversion and addition, the result is 834.585 minus J 404.396. Then, converting this rectangular form back to polar form, we find that the sending end current Is is approximately 927.398 at an angle of minus 25.85 degrees.
Now, moving on to question 3, which is the final question. We will use the previously obtained values to calculate both the line regulation and the efficiency of the line. Now, let's begin with the line regulation. This line is determined under no-load conditions and is calculated using this formula here, which is open bracket sending end voltage Vs divided by parameter A all minus the receiving end voltage V are close bracket divided by receiving end voltage Vr times 100. Substituting in the values, line regulation equal open bracket 233,547.709 divided by 0.9917 minus 190,525.588 close bracket divided by 190,525.588 times 100. Calculating this gives a line regulation of approximately 23.6%.
The efficiency of the transmission line can be calculated using this formula. That is the receiving end power divided by the sending end power, multiplied by 100. The receiving end power is already known to be 480 megawatts. To find the sending end power, we use the previously calculated values. The sending end power is equal to the square root of 3 multiplied by the line voltage, the line current, and the cosine of the phase angle. In this case, the line voltage is 404,516.497 volts. The line current is 927.398 amperes. Again, it is worth noting that in order for us to determine the correct power factor of the transmission line, we will need to add the phase angle of voltage and current at the sending end when added. The angle of the line is 33.12 degrees, and the cosine of 33.12 degrees is approximately 0.83. Therefore, the sending end power is equal to the square root of 3 multiplied by 404,516.497, multiplied by 927.398, and then multiplied by 0.83. This will equal to the sending end power of approximately 539,313,277.489 watts. Finally, the efficiency is calculated as 480 million divided by 539,313,277.489, which equals approximately 89%.
Wow, we've reached the end of another lecture today. In the upcoming sessions, we'll be exploring how to use exponential form to solve problems related to long transmission lines. Until then, peace.